So good morning. Welcome everyone to our department seminar series. Today we are pleased to have Dr. Ken Harrison as our invited speaker. Dr. Ken Harrison is an operations analyst at the Community Resilience Group in Engineering Lab at the National Institute of Standards and Technology and leads the first generation Community Resilience Systems Model project. The project involves the development of an optimization-based decision support tool for community resilience planning. In addition, Ken leads a national windstorm impact reduction program project in the Hurricane Maria program that examines the impacts to and recovery of distributed infrastructure supporting critical buildings and emergency communications. Ken joined the NIST from the University of Maryland and NASA, where for 8 years he worked on NASA's biological sciences as a research scientist affiliated with Maryland's Earth System Science Interdisciplinary Center. At NASA, he designed and implemented the uncertainty estimation subsystem of the NASA Land Information System software and conducted research investigating the value of NASA science satellite data for reducing hydrologic prediction uncertainty. Without further ado, I invite Ken to start his presentation and tell us about his interesting project.
Well, that's great. That was longer than I. That's great, Shima, and thanks for inviting me. I think it's exciting that you guys are close by to NIST since you're in the DC area. So I think that's great for collaboration if it comes to that. Yes, I'll mostly be talking about a model that is in development. We have a beta version, but it's a continuing effort. And we're located in NIST in the engineering laboratory, which is known a lot for helping out in the standards development for buildings. But they have gone into this area of community resilience as they figured out that whether a community recovers and how they recover goes well beyond just building damage. So this is the trend that we're caught up in and was amply demonstrated last week, of course, with the cold snap in Texas and other areas in the South and so on. So it's always an active topic. So I want to describe to you. Yes, I'm in the NIST engineering lab, and we do have a goal to promote economic security, and that includes sorry, a little problems with the advancement. But so we know why this is an important topic. We just saw it last week. We saw it in big time in 2017 with all the damage and, importantly, the displacement of survivors. What is resilience? It's quickly recovering, bouncing back, if you will, from disaster. And there's a large focus on planning ahead of time. So what is our role at NIST? Our role at NIST is to provide guidance metrics and tools. So what I'll be talking about today is an example of a tool in development. And I think what makes it a little bit different what we're trying to do compared to some other efforts is that we're really trying to link all the built environment, the engineering, if you will, to the actual goals of society in all of its forms. And so while we have, initially we had a lot of guidance on the right, our little 6-step, we have a guidance document. And where does the tool I'm describing today fit in? It's really, once you have all the stakeholders at the table, how do you get them together and work through this very complex problem of community resilience planning? So we have a number of projects. So when I joined, I was on an existing project for modeling of community resilience systems. But it's important to note too that we have a lot of other efforts. One, we have this large center of excellence that we fund out of Colorado State. So they're doing a lot of research and developing a similar, but with different aims tool or different design. So we have the planning guidance. We have a metrics project, equally important, where we have to ask questions. What you'll see is that our often engineering focused world needs to be expanded to include a lot of social systems, and that's where some of that fits in. And we have an economics office where they're interested, and they too have tools. All of these different areas have tools associated with them. I did want to mention, since we're at a university and you have many graduate students, that we really are a growing program. So we started with funding that large center of excellence for their 10-year project, but we're also building our internal capacity, and we have a variety of means to do that. And we will have an upcoming new direct hire too within the next month or so. So that's something to keep on the horizon. Okay, so what is this? What is this tool that I'll be describing? It's an interactive tool. The whole goal is to come up with a set of actions, not just one. We're not handing off the best solution, but a set of options to meet resilience and cost goals, given a whole slew of data on interdependencies and other data, kinds of data. A main point I wanted to make today is that, and I think this distinguishes it from some other efforts, it's really informed, the modeling is really informed by the getting out into the field with multidisciplinary teams and studying what happened, what slowed down recovery. And so we have this disaster and failure studies led by Maria Dillard in our group. And there, so under that program, and it's fun, I get to participate occasionally. We go out after a disaster, after they're done with the emergency phase, and we figure out is there anything to learn here, essentially. And sometimes there is, and so sometimes it begets a project such as the Hurricane Maria program, which occupies 50% of my time. So we see that there's something to be learned here. And for this particular effort, there's something to be learned for the modeling. Another example, and this is a collaboration with the Center of Excellence, and that is we work together on this longitudinal study where we're revisiting the city of Lumberton in North Carolina. And while I'll be a lot of things happen in Lumberton, North Carolina, I'll be focusing, just for the purposes of delivering this talk, on the water treatment plant system and some of its interconnections with the rest of the city. But our ultimate, we really do get out into all of that is implied by this figure. A lot of different systems in the community went down. So with that in mind, so what about Lumberton, North Carolina? It really was a struggling community. A lot of textile mills had left, poverty, triple the national average. So when this storm came up the coast in October of 2016, what happened was that there was a lot of flooding. To make matters worse, 2 years later, if you recall, Hurricane Florence, so we had Hurricane Matthew in 2016, then we had Hurricane Florence 2 years later, and it was nearly, in terms of the flood stage, it was virtually identical, believe it or not, to the Hurricane Matthew event. So it was a lot of water, and this even gives us a chance to see how some of the changes they implemented helped. But again, with the focus on the water system and how it impacts the modeling, that's the purpose of this slide. So if you go to that report, you can read various things. And again, I participated in a lot of this work, so I heard from the people who really had to deal under a lot of pressure with a lot of things happening. So for example, in the water system, they lost an intake pump, treatment plant generator. The Seoul water treatment plant was fully, as you can see in the figure, fully inundated. And it was interesting too, they had some protections in the community, a levee, of course. Some event, I call it event components, basically capacities that are brought in into play. So portable treatment plant trailers were brought in to treat groundwater, which is relatively clean, and they were able to actually get a lot of their system restored in a time that would otherwise have been impossible without that temporary capacity. Also, what do we want to capture in these models? It's important, it's seen from the field study, to capture startup times too. And then finally, it impacted the way I thought about how to even define recovery in the first place for the models that we build. But I want to make the point too that the impacts go far beyond the water system, or for that matter, transportation systems, the power grid. It goes well beyond that. So in this slide, I'm just showing a variety of pictures to suggest that, and mention some decisions, had they been taken ahead of time, could have averted what really was a disaster. So for one, there was a vulnerability in the levee, ineffective, the interstate served as part of the levee essentially, and it when the waters got to a certain height, there was a vulnerability in that there was a railroad cutting through under the interstate, and that's I-95 you're looking at. Had they had a floodgate there, they could have prevented a whole lot of suffering. Homes were flooded, many homes were flooded, and as the floodwaters raised, and of course, had they had mitigation measures in terms of, had they been built, for example, to a higher standard with respect to the elevation of that first floor of the home, that would have helped the situation. The treatment plant had certain control systems been elevated, or as FEMA recommended after, had they built a berm around the water treatment plant, it could have held on to the capability of at least the treatment plant, rather than relying on those portable treatment plants. And as I mentioned earlier, the surface water intake was out. So even if you had a functioning water treatment plant, you don't have the surface water intake, which was about approximately half of their entire raw water intake, the other half being groundwater wells that they thankfully had and were operable, enough of them. Electrical substation, had it been elevated ahead of time, it would not have flooded. Now they did have sufficient redundancy in the system. There were other City of Lumberton electrical substations, so fortunately this was not a major issue because they had redundancy. Now the schools, this was quite tragic really, in that they lost a lot of schools in these areas. And on top of it, I don't have a photo for it, but it was fascinating talking to just seeing how the impacts of this, if you think of the educational system, when we talked to the dispatch for the buses, the person responsible for that, they had to, people are displaced, kids are all over the place. And even if you had capacity for the schools, which they ultimately did have, they had to know where the students were, how to route them on their, to get them to these new schools. On top of that, they had to first ensure that the roads were safe for the school buses. So they had to work all that out. So a lot of impacts in Lumberton, and of course business impacts. The transportation system was evident from that earlier picture. So back to the model, how do we tackle the problem of community resilience? It's quite there's a lot of involved systems. It's complicated. So just to back up, what kinds of models can you contemplate for supporting decisions? And one approach is that we can develop simulation models. So if you tell the model what decisions you're contemplating, you can tell, if we have the appropriate metrics, we can tell, oh, what do we expect the cost to be? How will recovery times be impacted for an event. And of course, that can be expensive. Take up a lot of time because you have to manually adjust, as the figure notes, many such little slider bars. There's lots of controls in all of the systems that I've touched upon. And it's often not clear how to adjust those controls to achieve the outcome that you want in terms of cost and recovery, let alone investigate trade-offs. So we have optimization models, which I know many of you are familiar with in your program, where you flip it around. Hey, the user wants to achieve a certain set of objectives, and wouldn't it be nice to have the model predict what to do? And so I think of it as optimal trial and error. And we have efficient algorithms for that, and it facilitates generation of trade-offs. And within optimization models, we're further zooming in on what the tool I had a hand in developing uses. So we have MetaHeuristics, so that where we can pretty much use the simulation models we have, which capture a lot of the realism of our problems, but some of those methods are slower. There are trade-offs involved, and so the approach I took was to instead be willing to tolerate some loss of resolution, if you will, in the realism, in order to gain some amount of interactivity. And so the approach I took was one of integer linear programming. And just one additional note on the so we're taking this mathematical programming approach. This has a nice and storied history, lots of application across all sectors, including public sectors, and a whole range of interesting problems. Again, I'm talking to a group that knows all of this, but I did want to drive home this point, because I get asked a lot why the center that we're funding is going a different route than the one I'm taking. And it's really about trade-offs, and we need all the solutions on board to really tackle this problem of community resilience planning. It requires research. So yes, there's trade-offs in model precision. We want to capture realism, and it's solution time. And so we know, for example, linear programming, you may have to linearize some functions, but you do that so you can gain some speed of the solution. Also, there are consequences to, if we use a meta-heuristic, we don't necessarily know that we're getting the optimal solution to the problem as it was described, although since it has more realism, perhaps it's a better solution. Or we have, in the case of linear programming, we have some guarantees on optimality, but then again, it wasn't the problem. You made approximations to the problem. So a lot of trade-offs involved. And I'm throwing this on there too. You see a lot of resilience tools that look at connectivity, solely connectivity, which is fine. That's another set of trade-offs. It's obviously lacks some of there's no flow, for example, in some of the resilience approaches, but it is attractive for these other reasons. They're more tractable to work with. So INCORE, the centers tool that we fund, makes a certain set of trade-offs, and then ARC makes a different set of trade-offs. This is my literature search slide, if you will, as I described to people not in the field of math programming. A lot of motivators for the research, and many of you, by the way, probably know this area better than I do. I've been in this field for 4 years. And so you probably know better than I a lot of the literature. I'm still getting up to speed. But from what I can tell, yes, we have that on the one hand, connectivity in the system scope, and we have connectivity. And then you see a lot of work, including Elise Miller-Hooks and others in Shima on multiple infrastructure systems. And often they are infrastructure-only systems. Although even Shima, I remember you presenting work on social vulnerability, and so there are increased ties to social systems, but often what you see are infrastructure systems. Then we have these different levels of modeling precision, all the way up to full physics. The temporal scope is interesting. Some studies are only mitigation, focuses on mitigation, some only recovery. Some look at both, including in Elise's work. And some look at recovery, a single event, whereas others might look at multiple events. So where does ARC fit in there, this model that we're developing? It looks at, the real aim was to capture a broad system while making approximations. So it's a flow-based network. It doesn't include all the physics. And I felt it was important to include multiple events. So when we're searching for mitigation decisions, we ought to consider the very rare events, but high consequence events, and the more common ones too. So it's a flow network. This is a mini example based off of the Lumberton example. So it has substations and treatment, water treatment plants, surface water, groundwater, water distribution and utilities and so on, and then temporary components in gray, the mobile water treatment plant. So it's a network. It's a network. How does so I wanted to describe what is the deal with the network? How does a node lose function? And so here we have a storm, say a Hurricane Matthew come in. How does a node actually lose function? Well, you can lose it if that node is damaged. And so we have loading of the, in this case, the flood, this flood example, that loading is in the form of the elevation of the flood. And then we have, if that exceeds the resistance, which again for flooding is generally just the elevation of, say, an electrical control system. It's just elevation. So it can lose function by being damaged or losing an input. And it's important to note, and this adds to a lot of binary variables in the model, but loses an input, that's one way, but it may be the case that you can regain the input before the backup of that input runs out. So if you're a hospital, hospitals are required to have a certain amount of water on hand, certain amount of power generation and fuel, or fuel on hand in a generator. So there so that's important to capture, I felt, within the model. Now, when does a node that lost function get its function restored? It's the later of whether the lost inputs are restored or in the time that the damage is fixed. Okay, and if it is as lost function, it's important to add the startup time. So this is a big deal. In fact, it's playing out in Texas, I imagine, right now. When you have a water system down, then you really have to flush out you see all these boil water advisories, even after they're able to deliver the quantity and pressure, because they have to ensure that the infiltration of water, bad water, contaminated water into the system is flushed out. So you'll see startup times is a concept that figures into the modeling. Now, when is the community recovered? In the current model, we have when the user specified minimum demands are met. So for example, in that network, that utilities node could be the hospital. When it gets a minimum level of power, minimum level of water, we say it's recovered. And that's a user-defined notion. And it can be placed on multiple nodes, need not be one node. But it's important to note too that it doesn't rely, so the Lumberton system was recovered with those temporary measures, the portable treatment plants, and in not having to rely on the very damaged water treatment plant. So back to this network, what we see here is that here an event has occurred, say a Hurricane Matthew. Many things were damaged, that's shown in red were damaged, but we have the ability in the way just described to compute recovery times. of and what's shown in blue is what actually was used to stand up the system. And again, this is a schematic here. I wanted to give a sense of the data. So this is, you just read random ones. It's a bit overwhelming, the slide, but we have a whole bunch of sets in the underlying optimization model. So we have hazard events. We have those protections, the levee protecting, for example, the water treatment plant berm, potentially protecting the water treatment plant, for example. We have a bunch of cost information for increasing resistance and for adding new storage, backup storage. And then probably the most important assumption, or one of the important assumptions, is that we do have fixed recovery times for the nodes. And this was impacted also in our interviews with some of the leaders. For example, the water treatment plant operator had estimates for fixing the plant, irrespective of how many. So it's not, there is no crew assignment problem here. So that is a limitation of the model, is fixed recovery times. If something's broken, it takes so long to repair. I did want to emphasize that it is a two-stage program. So the first stage is where to increase resistance, where to, across this network, where to add backup storage. And then looking at, but then you have your recovery costs. And of course, if you're taking mitigation actions such as increasing resistance, you'll have a better outlook for a range of N events. So the overall problem is we can have cost constraints and recovery time constraints, but the decision problem, where to add resistance and increase backup storage. The whole purpose is to have this be, that model be put into a usable, interactive tool, one that allows the user to set objectives and constraints, run the model, but then to visualize the solution. And I have and then talk about trade-off curves and generating alternatives. But I do have a demo on the next slide, and you'll hear me inartfully going through the demo because there is audio that I hear. So it will be a little rough, and this is I took a 4-minute thing and really shrunk it down to 2 minutes, just cognizant of the time you have. So you'll see just flashes of capabilities. So it's not the perfect demo, but I wanted to give some sense. So this, and you can't, I just want to confirm you can't hear that, most likely. So what we have here is the ability for the user to say, what is the objective? What is our budget? Here's a $5 million budget. And so it's simple to generate a new solution. Then we have some capabilities to view the solution at a granular level and see what, here of this budget, how much goes to the water treatment plant firm, how much goes to elevating that electrical substation. And what happened in Lumberton, they didn't like an aspect of the solution. And so what we have is the capability to go in and actually add a constraint saying, you know what, we don't like that solution. We get rid of it, rerun a new solution, give it a meaningful name. They drive out the berm. So we have some visualization capabilities to compare across the different solutions and investigate and understand. So the whole difficulty is conveying to the users the differences in solutions and to incorporate what they do or don't like. So here's a lined up set of solutions, $5 million budget with no berm, and one where we force in something into the solution. And then a way to look for particular events, to look at what's going on, to understand differences and how those 3 different solutions perform with respect to different events. So we have damage represented and the ability to look at recovery times of individual nodes. And then finally, we have a trade-off curve tool, so we can automate, of course, how that generation of a trade-off curve. Oh, sorry. So yeah, that was the our demo from last fall. We made some improvements since then, but I think that the keys are, our whole goal is to make it interactive. So it's really quite quick. That was the original, about a 10-minute video where we're just walking through the process of the user doesn't like something in solution. How do we address that? How can we run it again, incorporating that? And just a note for this crowd, I wanted to put in this slide, you know, how do we implement this? Well, what it actually, as we're learning what a user interface might look like, we actually use some user interface tools within, I don't know if you're familiar with this, the Jupyter notebooks. I wasn't familiar with it, but our Center of Excellence uses it, and it's quite a nifty tool for prototyping different user use cases, essentially, for the user. And it sits upon there's some Python code that we have, and that sits on Ample, if you're familiar with that. It's kind of like GAMS. It's a modeling environment that can kind of separates you from the underlying solver, so we can test different solvers, and we use FICO in our group. So yeah, we have this tool. It's designed for interactivity, and what we're doing now is making it easier to install, easier to use, but also making it more capable, meaning expanding it to include more of the relevant aspects of the problem. So I want to take just a second here to say what the other ongoing research, and still sticking with the Lumberton example, is occurring. So we have this longitudinal study. We had not one, but two hurricanes that occurred. And so every year, essentially, we've gone back and revisited, and we're right now conducting interviews and surveys, importantly, the surveys. And this is the next two slides discuss the housing and business surveys, and what we learned through it, and how we wanted to discuss and bring to your attention how it is that, how we need to expand our models in these areas. So we have some interviews with schools and other local leaders, the city manager, treatment plant operators, but we also have surveys of those in and outside of the floodplain to see how their recovery to see how the residents' recovery has progressed, and the businesses. And again, we do this every year. So I wanted to share some conclusions. So it's interesting to me, and I think a lot of the engineering world work that predated this often looked at housing damage, and that was the end of it, or building damage. But what we're finding from these studies is that yes, the damage level can determine how fast recovery happens, but it doesn't have a significant effect on when repairs are done. And it does depend on the race and ethnicity are predictors of how fast recovery gets done. And then there's insurance figures in, household income. So all of these factors have to be brought into the model, and that's what we're currently doing now, getting housing into the model, and these factors on recovery times. We want to not say when is that utilities recovered at the hospital alone, but for all of this housing, when are people actually back into safe housing? And then there's the business survey, same thing. Based on the surveys, can we tell what are those predictors that interrupt businesses? And of course, we add building damage in there and that sort of thing, and how long it took to recover the water and the sewer operation. But we also have other issues: employee transportation access to the businesses, and employee health issues. And on a personal note, I participated in these surveys, and I got to tell you, it's heart-wrenching to hear, and also encouraging though to hear the struggles. Most communities fail if they can't go without 2 weeks. If it's beyond 2 weeks, this is what I hear from the social scientists, businesses start failing, and many either they lose their actual business, or they lose customers because the customers are displaced or in economic bad shape. So this is the final slide that I have. I didn't share much of the formulation. We can always talk about that. But what we're really doing, I have a link to the model as it is now, and we should have a slightly easier to install version in a month. But I wanted to make the point that at NIST we have this modeling effort and all these other efforts, the center's effort, the guidance. We have the metrics project focuses on those attributes that can really impact a community's resilience using broad, nationally available county level data, for example. We recognize the economics program really focuses on that it's not all about resilience. We're talking about city planning really, and resilience is but one aspect of that. So actually this year we're coupling the tool to a economics tool called EDGES, which can lend additional consideration of externalities into the process. So really, any help that you guys can offer, and formulation-wise or modeling insights, is of course appreciated as we grow this model to include all that is suggested in this figure: our transportation systems, our business modeling, and so on. And so I think I'll leave it at there, Shima, and take any questions.
Thank you, Ken, for that great presentation. I see one question in the chat box from Lynn Wells. Have you considered cyber resilience in the model?
No. I'm laughing because NIST has I don't know if you have exposure to it, but I hear all businesses comply with cybersecurity framework that NIST is actually, it's a pretty well-known program, and businesses have to incorporate it. But no, we don't. But the framework is general. There's nothing saying you can't bring it in, but it's not in a case study yet. And I don't know what the specific modeling issues would be for that. So no, it's not currently in there. But whether the existing framework can sufficiently model it, I don't know. That's a good question, though.
Just one of the things, Ken, that we've been looking at is we're calling adaptive compound threats, and the issue of cyber in conjunction with some sort of a major natural disaster where the cyber attack might be kind of hidden, if you will, amidst all the distractions going on from the other thing.
Oh, yeah.
The other question was Lumberton, Missouri. Joplin, Missouri is actually a pretty interesting case study of a totally destroyed community that kind of rebuilt itself. And I just wondered if there are any lessons from Joplin that could have been applied to Lumberton.
Yeah. So actually, we have in the NIST Center that we fund, Center of Excellence out of Colorado State. That is one of their test beds. Actually, it's a Joplin test bed. So we are well familiar with that, and it was prior to the Hurricane Maria investigation. That was a NIST investigation that led to a lot of. We still are involved in and on the hook actually for helping improve building standards with respect to tornadoes nationally. So we're on the hook for making sure that research is progressing in that area. We have in the plans actually for Hurricane Michael to apply this in a wind case study. That's a hurricane, a little bit different, but it was a large wind event. So yeah, we're familiar with Joplin, and it did wipe out a lot of the really significant buildings So, and we've learned a lot about the hazard side. There's a power model too for tornadoes that was developed off of that Joplin work. So thanks for bringing that up.
And just the last thing, we at Mason are doing a lot of work with Puerto Rico and Maria Rico. Oh. I'm particularly working with the Puerto Rico Science, Technology and Research Trust on the two things. One is the role of digitization in Puerto Rican reconstruction, but the other is how you do kind of cutting, coordinated, synchronized, integrated approaches across infrastructures. Like, I mean, if you're doing anything with power, and which Puerto Rico's not doing a lot of English and stuff with power, you have to be thinking about comms, and you have to get comms to run. And if you're going to do a road project, you might as well trench the roads and put the fiber and the power underground. And so, how do you get that transit thinking into the
Yeah, I didn't catch all of what you said just from the audio, but I got the gist. Comms and fiber.
Comms, power, transportation, just integrating across the different infrastructures.
Yeah, it's key. And so what we're doing for Hurricane Maria, what I'm doing in the infrastructure project is, obviously it's a huge problem to tackle, but we're actually have surveys that will be administered this year to get at a lot of the interdependencies between power, water, and transportation. So we have that effort, and we do have a wireless communications project. But I think it's very important, the communications, which is not a part of our project just for scope reasons, but it's so important, and it just, for obvious reasons, is important, and the resilience actions that should be taken have to address that. I mean, even the main power company didn't have access to their headquarters. No one could communicate to anybody. You had people trying to catch a signal, wireless signal, and then clogging up roads, and just a whole sort of nest of problems, really. So it's important. The communication system is terribly important, and the SCADA systems and all that.
Thank you, Ken. I see another question from Professor Kathy Lasky. Who are the intended users of ARC?
Oh, yeah, that's a good point. I should have mentioned. Yeah, so back to that guidance, we are recommending that communities and they typically are ones that were affected by a disaster. They're the ones typically planning and doing the planning, although that should not be the case, really. But so we have this notion of a community planning team, and so ultimately, I want a sophisticated user. That might be whether through university, a consulting firm, through us in the next few years, help work with the community to explore the different options available through this tool. Now, in the short term, we're trying to get this into some classrooms, so we expect that the users will be more academic. So I'm working with NC State to get it used within a class. And Zainab, who I believe is on the line, she's starting up a class working on getting it a class at Maryland and at University District of Columbia. But that's where I see it playing out. But really, it's communities who are planning. And one thing I did emphasize that we have in there a way to use the optimization model to generate distinct looking alternatives. So we actually optimize difference. We drive out what was in a solution while still meeting within a margin the cost and resilience objectives, recovery objectives. And so the real goal is provide alternatives so a stakeholder group can evaluate them for other objectives not in the model, of which there are many, many.
Yeah, so from what you, the demo that you showed me, it looks like you need to be a fairly knowledgeable user with regard to the models and modeling methodologies. And you also need to have a fairly good comfort level with sort of academic, not built something that's still a little rough around the edges, I guess, in order to use it right now. But it looks like something that could be ultimately potentially turned into something that community managers could use, but that it looks like it still needs some work to be able to do that. And then also you need to sort of bulletproof it against, right now, if you don't know anything about optimization and simulation and OR modeling, you could get yourself in trouble.
Oh yeah. So what it is right now is, and Zainab has done this, really contributed a lot to the interface develop. Just it's a great way to prototype. But in these notebooks, we can have those, sliders for the budget, but what we can't do, the whole point is to be able to incorporate things that we're not expecting the user to express. So we try to anticipate. But we also have the ability within the cells of the notebook to actually modify it. And that's really where that sophisticated user has to be, that someone says something we don't expect, that we have to be able to add the constraint essentially, and then do a run with that constraint in effect. So I completely agree. And we also need to have more interactions with users too. And so that's in our plans over the next couple of years, getting more users involved so we know what changes need to be made.
Thank you. Any other question from the audience?
This is John Tortle. You mentioned low probability, high consequence events. How much of a probability are considered in the model? And can you say more about how sort of probabilistic elements might be included? I understand it was more of a deterministic model, but the Center of Excellence was using a different approach, or maybe say more about the simulation approach.
Yeah, great question. So right now, what we have in the formulation, we have the different events. So the uncertainty that's in the model is really are the probabilities of those different events. So I'm relying on, because I know there are other groups working on such things, and that is I do not anticipate this model to have the hazard modeling as part of it. So what has to be handed to the model are a set of events and their probabilities. So that's on the hazard side. Now, Zainab, who I just mentioned, and you're welcome to chime in, Zainab. Actually, I can stop sharing now too, just occurred to me, since we're discussing. So Zainab is actually developing a post-analysis tool. So we can look at, bring in after the fact, the uncertainty in those duration times, some of the critical path like duration times and cost for that matter. And over time, we can bring in some of that into the optimization framework itself. But if we, so she can put in there, if we had to linearize some cost function, she can have that in the post-analysis piece and report that out. So that's what she's aiming at. Yeah, she's on the call. Can you wave, Zainab, just so people know who you are?
Yeah, sure. Yeah, thank you for the explanation, Ken. Yeah, that's it. And yeah, that's we are going to get all the uncertainties, and then we will incorporate to the model, and then so at the end, instead of just deterministic model, we have incorporated all the uncertainty, not just the hazard model. For all the parameters, we will consider a range.
And another thing that's interesting is that a lot of these, we have to be careful about how we model the low frequency, low probability events. And so she's also looking at importance sampling and related approaches. Because if you're planning on levy failure, if you're just doing crude Monte Carlo simulation, you have a limited sample size, you may not hit that levy failure. So we want to look at techniques that will oversample those and get that right. So it's endless work for Zainab. And I should say Zainab is well, what is your official position at, I was going to say faculty, but.
Research faculty.
Yeah, research faculty, but Zainab loves teaching, and so which is great. So that'll help immensely getting it into the classroom.
Thank you. Great. Any other question? So I see comments. You go ahead. Okay.
Yeah, I don't see personally.
Okay, good. So from Kathy, she thanks you for a really interesting talk, and this is a useful tool. Same Ken for the informative presentation. So if there is no other question, I think let's give a round of applause for Dr. Ken Harrison, and I hope you all enjoyed the rest of your day. Thank you.
Thank you all. Have a good Friday. This was fun. This is the most fun since the pandemic.